Right. Good afternoon, Year 10. So what we're going to be doing today is we're going to be looking at momentum. But before we do, we're going to go back and mark the questions that we did on Wednesday. So I'll go through the answers with you and then I'll upload those for you as well. So these are all exam standard questions, which means what you need to do is you need to make sure you're using technical language in order to answer these. So the first question was define the following terms. These were level 4 to 6. And thinking distance, that is the distance travelled during the driver's reaction time. Okay, now again, look at the definition of it. The distance travelled during a driver's reaction time. Braking distance, the distance travelled while under a braking force of the vehicle. Again, look at the language that they use. The distance travelled under a braking force. How do you scientifically define braking distance? Okay. The question 2 says the thinking distance for a driver in a car travelling at 40 miles an hour is 12 metres. The braking distance is 24 metres. Calculate the car's stopping distance when it's travelling at 40 miles an hour. Okay, so quite straightforward. You need to add the thinking and the braking distance. So it's 12 metres, add 24, 36 metres. Okay, so don't overcomplicate it. It was a level 4-6 question, straightforward. Question 3. When a vehicle's brakes are applied, energy is transferred away from the kinetic energy stores of the wheels. State what causes this and describe the effect it has on the brakes. Okay, so again, we need to think about this one. So, state what causes this and describe the effect it has on the brakes. And as you can see, it's level 6 to 7. So work is done by friction between the brakes and the wheels. So you need to identify that energy is transferred, basically kinetic energy of the moving car to thermal energy as heat is generated by the brake pads pressing together. So basically energy is transferred, so therefore work is done by friction between the brakes and the wheels. This causes energy to be transferred to thermal energy stores of the brakes, so the increase in temperature. Now that was worth 2 marks. So again, it's this idea of understanding that work is done. Energy is transferred from the kinetic energy of the car to the thermal energy stores in the brakes. Okay. Right, now the next question, question 4, it says explain the importance of a car having brakes and tyres that are in good condition and the effect this will have on stopping, distance and safety. Now again, this was a level 6 to 7 question. So what you needed to do was identify, so each of these points would score a mark, and what you need to do is think about how these work. So firstly, a good tread depth on the tyre removes water. That would have got you a mark. This means there is a large amount of grip, friction between the road and the tyres. This decreases the braking and so the stopping distance in wet conditions. It also means the car is less likely to skid in wet conditions. Brakes that are in good condition allow a larger braking force to be applied. This means the braking distance of the car is shorter. Brakes that are in good condition are also less likely to overheat under a braking force, so the car is less likely to go out of control and cause a crash. Now, if you actually think about the question, explain the importance of a car having brakes and tyres that are in good condition. So, why is it important for a car to have brakes and tyres in good condition? So look at the explanations here. It means there's a large amount of grip, decreases the braking and so the stopping distance, okay? And then the effect this will have on the stopping distance and safety. So it's talked about the effect on the stopping distance. Look, the decrease of braking and so the stopping distance. And then it says, what effect will this have on safety? So the car is less likely to go out of control and cause a crash. Okay, so you need to think about, have you actually explained and answered the question? Okay, so pause the tape now, see which points you made in your answer, and if you didn't make the point, or if you didn't answer the question, or you struggled to answer the question, add these points in now in a salient sort of order. Okay, so you're looking for 6 clear points laid out in a clear and constructive way. Okay, so pause the tape now and give that a go. Okay, so on to the next page, page 66. What is the typical reaction time for a person? It is 0.2 to 0.9 seconds. Give 3 things that could affect a person's reaction time. tiredness, alcohol, drugs, distraction. 3 very easy marks to get. Again, these were level 4 to 6 questions, these first ones. A teacher tests reaction times of 2 of her students by measuring how far the ruler falls vertically before the student catches it. Describe one other method that can be used to test a pupil's reaction time. Now, what we were actually going to do was a reaction time experiment in the class. We were going to do the ruler drop, but also we could have used a reaction app on the computer. So clicking a mouse on a computer screen changes, or any sensible, reasonable suggestion to check reaction time, I would have accepted. Question 3.2. Table 1 shows the results. The values in the table show the distance the ruler falls in centimetres during each attempt. Complete the table by working out the average distance fallen by the ruler for each student. Okay, so this is just, can you work out the average? For student A, it was 7 centimetres, and for student B, it was 8.3 centimetres. So again, 2 fairly easy marks there. Question 3.3, which student has the fastest average reaction time, and give a reason for your answer. It was student A, because the average distance the ruler fell for student A was less than that for student B. Question 3.4, it's just 2 ways the teacher can make this experiment a fair test. Use the same ruler, always have the same person dropping the ruler. Now remember, it's very important in the exam that you cannot just say fair test without quantifying it, without actually explaining why. So never ever under any circumstances say to make it a fair test and hope it will score. It will never score a mark unless you quantify it. Right, 3.5, the teacher then repeats the experiment. This time she has a third student talk to the student being tested. Predict how this will affect the reaction times of both students A and B. The reaction time will get longer. As we know, distractions can increase your reaction time. Right, now for question 4, you needed to describe the steps involved when using the ruler drop experiment to investigate reaction times. Now this should have been quite straightforward because a couple of lessons ago I asked you to do this at home, so hopefully you simply describe it. But again, I want you to pay close attention to the detail needed. Now this is a 5-mark question, so hold the ruler between the opening forefinger and thumb of a person being tested. Again, look at the detail needed to describe how you're going to do it. Align their finger to the 0 line on the ruler, then drop the ruler without warning. That would get you another mark. Okay, so again, look at the detail needed. And have the test subject close their thumb and forefinger to catch the ruler. So you're basically just describing how to catch, but again, that's worth another mark. The distance the ruler falls can be read from the ruler, another mark. The time taken for it to fall can be calculated as acceleration due to gravity is constant. This is the reaction time of the test subject. So it doesn't tell you actually which equations you need. It just says time taken to fall can be calculated because we know the acceleration, which hopefully we managed to do last lesson. So that was worth 5 marks in total. So check through which points of those that you got, and if you didn't, please add those now. Okay, question 5. A man is driving home late at night. He listens to loud music as he drives to keep himself alert. He is impatient to get home, so drives quickly. Explain the safety implications of the man's action. Okay, so the safety implications of the man's actions. So you've got a few points here, 4 possible marks. So you could have any of these. Listening to loud music may mean the driver is distracted. That'll get you a mark. This may increase his reaction time. So you've said what will happen and an explanation why. An increased reaction time means an increased thinking distance. Okay. Driving quicker also increases the distance the car travels during a driver's reaction time. Remember what we said, if you are going faster, the laws of physics state you will travel further no matter what your reaction time actually is. If you're going faster, you will cover a greater distance. All of these things increase the stopping distance, which means he may not be able to stop in time to avoid hitting a hazard. He may not be able to see an upcoming hazard because it is dark. Driving late at night might mean the man is tired. He may not be able to hear an upcoming hazard because of loud music. This reduces the stopping distance required to avoid hitting a hazard and may lead to the driver having a collision. So once again, look at the wording, think which of those points did you actually use? Okay, it's really, really important that you study the mark scheme and look at the language which is used in order to actually get the marks. Okay, on to question 6. Now, again, this one we had to essentially apply the maths that we did the other lesson. So, a student tests his reaction time with a meter ruler using a ruler drop experiment. He catches the meter ruler after it has fallen 45 centimeters. Calculate his reaction time. The acceleration due to gravity is 9.8. Right, so we know that v squared minus u squared equals 2as. So if we put the equation backwards, v squared minus 0, y0, well, we know u squared is the initial velocity, and the initial velocity will be 0 because it's not moving. Add 2, there's 2, 9.8 acceleration, and 0.45 because distance is always meters. So that gives us 8.82. You can put that in test in your calculator. That would get you 1 mark. Then you have to square root it. So 8.82, so square root of 8.82 is 2.969 meters per second. So that's the velocity. There it is. Okay, that would get you another mark, 2 marks. Now, we know that acceleration is the change in velocity divided by time, so we need to rearrange the equation. So time is the change in velocity divided by acceleration. So therefore, acceleration is 2.969 divided by 9.8. Okay, so there's our velocity divided by acceleration. So velocity divided by acceleration, there it is. That's another mark if you put in that equation, which gives us 3.03, 4 marks, and then 2 significant figures, 0.3, final mark. Okay, so there it all is. That was worth 4 marks. Right, last one, on to question 1 on page 68, some more on stopping distances. So excuse the appalling line, I had to do this rather badly, but what you should have plotted the points there, and then your line should have been an upwards curve. Okay, any of you that drew a straight line, I'm afraid is wrong. It should have been an upwards curve. Okay, and if you need to check that, please go to page 69 in your revision guide and make sure you've got that, but it should have 100% been an upwards curve. Okay, right, next one, using the data in table 1, complete the graph shown in figure 1 to include a line of best fit. Okay, so that's very easy, done all of that. 1.2, using figure 1, stopping distance, find the stopping distance for a car traveling at 35 miles per hour. So, well, there's 30, 35, would have been about there. So you should have gone simply across there like that, read it off the graph, and anywhere, basically 30 meters was your actual answer, but anywhere between 28 and 32, depending on how you drew your line of best fit, is acceptable. 1.3, calculate how much further the car would travel before stopping if it was traveling at 65 miles an hour. So once again, well, there's 60, there'd be 70, so you go, right, well, there is your answer. So it would be somewhere up there like that. So you should have got about 83, okay? And then obviously it said how much further. So you minus the 30 that you already worked out a minute ago, or whatever your answer was here, and you should have got 53. So 53 or minus whatever your answer here was, that would get you your mark. And then finally, question 2, the stopping distance of a truck traveling 18 meters per second is 45 meters. The truck driver has a reaction time of 0.5 seconds. Estimate the stopping distance for the truck if it were traveling at 36 meters per second. Right, now this is quite tricky, so I'm just going to go through it with you. Okay, so question 2 was a level 7 to 9 questions. This is really quite difficult. So let's look at what we've got. We've got 18 meters per second, 45 meters. So the stopping distance for a truck traveling at 18 meters a second is 45 meters. So the first thing you would do is you need to realize distance, velocity, time. Okay, so 18 meters per second times his reaction time, 0.5 seconds, is 9 meters. So therefore his thinking distance is 9 meters. Okay, now this is where we need to be a little bit clever. Now, if you think back to what I said, okay, as the thinking distance, the link is directly proportional. I remember you should have drawn in your books a straight line that shows a link between stopping distance and reaction time. Stopping distance, yeah, and reaction time. So, and speed, sorry, not reaction time. So, here is the thing. He travels 9 meters, but remember, he was going, that's at 18 meters per second. However, if you look further in the question, it says, estimate the stopping distance if the truck were traveling at 36 meters per second. So, if it's 9 meters traveling at 18 meters per second, then hopefully, so the braking distance at 36 meters per second, if the speed doubles, the thinking distance doubles. So 9 times 2 is 18 meters. So essentially, it gave us a speed if it was traveling at 18 meters per second, but then it said, right, so what would be happening if it was traveling at 36 meters per second? Well, you need to double it, because remember, those lines were directly proportional. I asked you to draw these two graphs. Now, this is where it gets a bit more tricky. The braking distance, it doesn't double. Okay, it's not the same. It increases by 4-fold. Now, look at what they've done. They've worked out that the braking distance is 36 meters because look, at 18 meters a second, it stops in 45 meters. So we minus our 9. We're left with 36 meters. Okay, now we know that the thinking distance is 18 meters. There it is. And the stopping distance is 36 meters. But if the speed doubles, the braking distance increases 4-fold. Now, if you get stuck, please do have a look on page 69 in your revision guide to make sure you understand this. So, 36 squared times 2 squared is 144. So the total braking distance is 144. We then add that to the thinking distance, which gives us a total of 162. Now that was a 5-mark question. This question, obviously, you have to think quite laterally. So 100%, take the time to work it out yourself, please. Make sure you understand this one. Okay. Okay, so what we're going to do today is we are going to start to look at momentum. However, this is quite a complex part of forces. It involves 2 or 3 equations and probably an experiment, which we're going to do when we come back to school. So the first thing I asked you to do was try to define momentum. Okay, so a good answer, and I'd recommend you copy this into your textbook, is this. Momentum is the property of moving objects in a particular direction. It tells us how difficult it is to stop a moving object. So with that in mind, it should hopefully link your brain to inertia. So what I'd like to do is copy that definition down into your book. So pause the tape now, please, and copy that down. Okay, so the next thing we need to do is an example. So a rather grim example, but useful. How does a gun actually kill? So let's just take a typical gun like this, okay? What do we need to know to calculate momentum? What do we need to know about a moving object to know about its momentum? Okay, massive clue there. Okay, mass of the gun, mass of the bullet, and the velocity of the bullet. Okay, so what do we need to know about a moving object, an object, to know its momentum? Right, hopefully some of you have started to work this out. Now we're going to come back to this in a few minutes, okay? To calculate momentum, we do mass times velocity, okay? Now momentum is denoted with a P, so what I would like you to do is draw in your equation triangle as always and put everything in the right place, please. So can you just pause the tape now and do that? Okay, so there it is. So we know, therefore, that mass times velocity equals momentum. Momentum divided by the mass will equal the velocity, and momentum divided by the velocity will tell you the mass of the object. Okay, now there is a couple of really important things you need to know about momentum. Okay, so we're going to talk about the momentum of explosions and the momentum of collisions. This is what you sort of need to know for your exam. So, in an explosion, momentum is conserved. Right, now what does that mean? Essentially what it means is that the momentum before the explosion is the same as after the explosion. So let's just take, for example, two people on ice skates. Imagine them pushing against each other like this. As they push against each other, you can think of that as an explosion. Okay, so what we're going to do is we're going to put some values here for our two people. We call them Jack and Holly. So let me just explain what we're going to do with them, and I'll put some values in. Okay, so the golden rule of momentum is that momentum is always conserved. So we're going to start by putting in some values. So Jack and Holly start like that, and then they push apart like an explosion. Okay, so we're going to say that Holly's mass is 40 kilograms, and we're going to say that Jack's is 60 kilograms, bigger guy. Okay, now when they push apart, Holly flies off in this direction, so she's going in that direction, and she goes at 3 meters per second. Okay, now here is the question: can we calculate the speed at which Jack goes in his direction? Well, yes, we can, because what we can do is we can calculate Holly's momentum. Okay, so firstly, how do we calculate Holly's momentum? Okay, so 40 times 3, mass times velocity, gives us a momentum for Holly of 120. Now, we need to know a couple of things. Momentum has a unit, and the unit for momentum is this. It's a combination of mass and velocity, so it's kilograms meters per second. Okay, so that is the unit of momentum. So let's just put that in there. Kilograms meters per second, not kilograms per meters per second. Just make sure you get that right. So Holly has a momentum of 120 kilograms meters per second. Now, firstly, because we are doing mass times velocity, this is actually a vector quantity. Okay, that means she's going, let's just say, forward. So what I'm going to do is give Holly a little plus sign to show that she is moving forward. I'm just going to put that there. Okay, which means technically her momentum also gets a little plus sign because her momentum is forward. Okay, so there we go. That's Holly. Okay, she's got a momentum of 120 kilograms meters per second. Now, what was their momentum at this point? Okay, when they were just stood there. If you think of them together, their combined mass would have been 100, 60 and 40, but the velocity was 0. So 100 times 0 is 0. So their momentum before the explosion was 0. Now, I want you to bear that in mind. Now, here's the other thing. Whatever Holly's momentum is, Jack's momentum will be too. Okay, so firstly, let's put that in. Okay, so there's Jack's momentum. However, his is a negative number because he is going backwards. So his is a minus number. Okay, so now can we work out Jack's velocity? Well, yes, we can, because we do 120 divided by 60, but it's obviously a minus number. So Jack's is there's Jack's velocity. Okay, so we've been able to work out what their velocity is. So, a couple of little points. If we add together minus 120 add plus 120, what do we get? We get a big fat 0. So, momentum before the explosion was 0. The momentum after the explosion, after they push apart, is also 0. Okay, so what I would like you to do is pause the tape now and quickly copy that into your book. Okay, so let's go back to the gun example. Okay, so let's look at what we've got. We are trying to find out how a gun actually causes damage, how to actually kill people. So let's look at what we know. We've got mass, velocity, and momentum of the gun, and mass, velocity, and momentum of the bullet. So let's start by putting in the values that we know. Right, we know the mass of the gun is 1.5, so let's start by putting that in. It's 1.5 kilograms. That seems to be all we know about the gun at this point. Mass of the bullet is 0.005 kilograms, so that would be 5 grams. Okay, just move that slightly so we can see it. Okay, and do we know the velocity of the bullet? Yeah, 1,000 meters per second. So let's just put that in there. Okay, let's look at what we've got. We've now got the ability to calculate the momentum of the bullet. So let's start by doing that. So we'll simply bring up my calculator and we will do 0.005 times 1,000 equals, right, so it's 5. So in this case, the momentum of the bullet is 5 kilograms meters per second. Now, whatever the momentum is of the bullet will be the same as the momentum of the gun, because momentum is always conserved. So actually what we can do is we can just simply move that over here, and now we can calculate the recoil velocity of the gun. So we would simply do, just clear that, 5 divided by 1.5 equals 3.3 recurring. So in this case, the gun recoils speed or velocity of 3.3 meters per second. Okay, so here's a weird question. The momentum of the gun and the bullet is the same. It's 5 kilograms meters per second. So if it was momentum that did the damage, then that means that every time somebody fired a gun, the person doing the shooting, as well as the person being shot, would also suffer a fatal injury, because they have this bullet and the gun have exactly the same momentum, which is 5. Now, clearly that isn't the case. Okay, so the question is, why doesn't the momentum of the gun actually kill you? Well, we're going to find out later, but here's the thing. The momentum of both the gun and the bullet is the same, 5. Okay, 5 kilograms meters per second. You can see the bullet has a much greater velocity, 1,000 meters per second. The gun recoils with a speed of 3.3 meters per second. So you could certainly hold on to a gun at that speed. Right, so we're going to come back and actually answer that question probably in the next lesson. Okay, so just to finish off, I put an assignment into the assignments part. There's some questions on momentum. I'd like to give those a go and upload your answers, and then when I see you next term, what I will do is I'll go through those answers and then we'll finish off about momentum. However, this lesson is quite complex because there's quite a lot you need to know. But so far, the golden rule of momentum is, in an explosion, momentum is always conserved. Okay, so if the starting momentum is 0, the total momentum in both directions must add up to 0. So the negative momentum and the positive momentum should add up to 0. Okay, right, there is a little bit more on this in your revision guide. So what would be a good idea is to go to page 70 and have a look at that in your revision guide and make a few notes over the Easter holidays. Okay, I'll be online to answer your questions. Good luck.